because it's fundamental, I want to give us a section about G structures. Okay, so if we let X be an n manifold, an F of X, its frame bundle, which is a principal GL n comma R bundle. Let's now suppose that G sitting inside GL n comma R is a Lie subgroup. Okay, so a G structure is P on X is a principal subbundle P contained in F with structure group G. So what this means is that P contained in F is an embedded submanifold which is invariant under the action of G contained in GLNR. So GLNR acts on F, so therefore G acts on F as its a subgroup of GLNR, and the G action preserves P, even though the GLNR action generally won't. So invariant under the action of G, and then pi restricted to P, going from P into X, and the action of G on P make P into a principal G bundle over X. Okay, so it's a principal G bundle which is living as a submanifold of the frame bundle. So G structures are basically a very useful class of geometric structures on X. So to give you the idea, let's see how if we take G is O of n contained in GLNR. So then O of n structures are in one-to-one correspondence with Riemannian metrics G. And the correspondence is that P, the O of n structure P, is equal to the set of X E1 up to En in frame bundle F, such that the basis E1 up to En is orthonormal with respect to the metric G at the point X. So that's one example. Another example, if we take G is GL plus NR, which is a set of aij's in GLNR such that the determinant of the matrix is positive. So these are invertible matrices, so the determinant is either positive or negative. This is basically half of this thing, and then G structures are in one-to-one correspondence with orientations on X by basically P gets identified with a set of X E1 up to En such that E1 up to En is an oriented basis for Tx of X. Or another example, if we take n is 2m and we take G to be the group GL m comma c, thought of as a subgroup of GL 2m comma r. So GL m c acts on c to the m, which equals r to the 2m. That defines that inclusion. And then a G structure is in one-to-one correspondence with what's called an almost complex structure. J on X, which we'll come to when we talk about complex and Kähler geometry. So basically, any Lie subgroup G sitting inside GLNR you can think of, that defines you a notion of a geometric structure, a G structure. Usually it's interesting to think about G structures satisfying a partial differential equation. So for example, if you've got an O of n structure, that gives you a metric. The metric gives you a connection, nabla the Levashevsky connection. You can then start asking for example, curvature conditions or whatever. For the case of almost complex structures, there's a torsion type invariant called the Neuenhaus tensor. You can ask that to be 0, then it becomes a complex structure. So a good way of encoding a lot of the stuff we talk about in Kolomny groups is in terms of G structures, and G structures satisfying partial differential equations. But maybe we'll come to that later. Okay, so now let's start a new section 2 on holonomy groups. Which is the main subject of the lecture course. And we'll begin with the subsection 2.1 on parallel transport and holonomy groups. So the holonomy group is something you define whenever you have a vector bundle and a connection on it. Actually, you can also do it whenever you have a principal bundle and a connection on it. But we're mainly going to be interested in the case in which the vector bundle is a tangent bundle and the connection is a Levashevsky connection of a metric, in fact. But we'll start off with the general case. So if we let big X be a manifold, and actually let's say usually connected, because actually if the manifold is not connected, you're going to get a different holonomy group for each connected component of the manifold. So it's simpler to suppose your manifold is connected. And let's suppose that E over X is a vector bundle of rank R. So the fibers are R to the R. And nabla is a connection on E. So So let's suppose that little gamma going from the closed interval 0, 1 into x is a smooth path. Actually, we want a little bit more generality than that later. So more generally, piecewise smooth. So what piecewise smooth means is that you can divide 0, 1, the map gamma is continuous, and you can divide 0, 1 up into finitely many intervals, closed intervals, on each of which the thing is smooth. So then you'll get some finite number of points in the middle of 0, 1 where the thing is, which are the junctions between the two intervals, where, so I'm thinking about something looking a bit like this. If some finite number of paths, we allow there to be a finite number of internal points inside the interval 0, 1, at which the thing has a left derivative and a right derivative, but the left derivative and the right derivatives need not be the same. Okay, so you can have kind of angles. This would be piecewise smooth. Okay, gamma is a smooth path, or piecewise smooth. So then the parallel transport map, well, P gamma, this maps from the fibre of E at the point gamma of 0 into the fibre of E at gamma of 1. So it maps from the fibre of E at the start of the path to the fibre of E at the end of the path. It's an isomorphism. These are vector spaces, finite dimensional vector spaces of rank R. This is a linear isomorphism. So these are vector spaces isomorphic to R to the little r. And here's how we define it. So defined as follows. So for each point in the domain, little e in big E at the point gamma of 0, there exists a unique smooth, actually, or more generally, piecewise smooth. So it's smooth if the base curve is smooth, and it's piecewise smooth if the base curve is piecewise smooth. Piecewise smooth family, little et in big E gamma of t for all t in 0 up to 1, such that the derivative in the direction d by dt of et equals 0 for all little t in 0 up to 1. So what's really going on here is that over x we've got a vector bundle E. We can pull that vector bundle back to the interval 0, 1 using gamma. So that now gives us a vector bundle over 0 up to 1. There's a connection on that. The connection is also pulled back by smooth maps. So there's a pullback connection on here. And so this is really saying that the section ET is constant under the pullback connection. E at the point 0 is little e. So that just holds by results on ordinary differential equations. So we're trying to solve a first order ODE with initial value E0 is E, and it's basically, if you write this out in coordinates, it's of the form d by dt of et is some smooth function times et, and then Picard's theorem or whatever it is will tell you that there exists a unique solution of that kind. The thing can't blow up because the growth would be at worst exponential, and exponential things don't blow up on finite intervals. And then we set p gamma of E is E at the time 1. Okay, well, so usually we're going to take E is Tx and nabla is some Levi-Civita connection of some metric G. Yep.
One comment. Strictly speaking, ET is not a section like we're using.
Well, the map from T to ET is a section. Okay, yeah, well, think about that as all of the ETs, the family of ETs. Yeah.
So you're putting the connection back to the interval?
Yes, you can pull the connection back to the interval. I didn't tell you how to do that. Or you can think about it as somehow differentiating just in some direction on the manifold X. Okay, so, well, if you've got a manifold X, and you've got a path gamma, there's gamma of 0, there's gamma of 1. You've got another path delta, which starts where so we can compose paths. So if gamma and delta map 0, 1 into x, with gamma of 1 is delta of 0. These are, well, piecewise smooth. With gamma of 1 as delta of 0, so the same endpoints. Then we define delta star gamma, which means delta comes after gamma, mapping from 0, 1 into x. Well, so if I always take my interval between 0, 1, then I need to change the speed of these things. So basically we first do the path gamma twice as fast. So we take gamma of 2t, and that's for t in 0 up to half. And then after that you do delta of 2t minus 1, and that's for t in half up to 1. And at the point of half, these give you the same thing because gamma of 1 is delta of 0. And you can see that even if you started with gamma delta being smooth, delta star gamma might be piecewise smooth because they might come in and go out in different directions. So you could have an angle there. And so then you can check that P delta star gamma is P delta composed with P gamma, because, well, parallel transport doesn't really care about doing something twice as fast. Also, we can also define a path minus gamma going from 0, 1 into x just by doing gamma in the opposite direction. So minus gamma of t is gamma of 1 minus t. and then P of minus gamma is P gamma inverse. Okay, so if you go the opposite way along a path, then you invert the power transport map. Okay, so now let's fix a base point. Little x0 in big X. So I'm going to define the holonomy group at a fixed base point, but it's going to turn out that the holonomy group doesn't really care about which base point you choose, at least provided X is connected. So let's define the holonomy group big hole of nabla to be the set of all parallel transport maps P gamma such that gamma going from 0 into 1 into X is piecewise smooth and gamma of 0 is gamma of 1 is your favourite base point x0. So we're thinking about loops which start and finish at x0. In manifold X. And this is contained in the group of automorphisms of E, the fibre E at the point x0. And because we supposed E has rank k, this is isomorphic, though not canonically isomorphic, to GL k, R. Okay, so we're defining this thing basically initially it's just as a subset of the Lie group GLKR. So let's look at some basic properties of this. Okay, so firstly, an important thing. The holonomy group of connection nabla is a subgroup of ort of E at x0 isomorphic to GLK, R. The subgroup, well, that's because it is closed under composition. So it's closed under composition because P of delta composed with gamma is P of delta composed with P of gamma. So any two elements of this things are of the form P delta and P of gamma, and because they have the same endpoints, you can compose the loops, and then delta star gamma is also one of those. And it's also closed under inverses. And that's since P of minus gamma is P gamma inverse. And a subset of group which is closed under composition and inverses is a subgroup. Secondly, the holonomy group of nabla is independent of the base point little x0 in big X, at least if big X is connected because if little x0 and little x1 are points in X, and well, then if we assume X is connected, it's also path connected, so we can choose some smooth path, piecewise smooth path. Gamma 0,1 into X is piecewise smooth with gamma of 0 is x0, and gamma of 1 is x1. So we've given any two possible choices of base point. You can choose a path between them. Then we have a parallel transport map. P gamma maps E at x0 into E at x1. The holonomy group at the base point x0 of nabla, you can check, is equal to P gamma inverse of the holonomy group at the point x1 of nabla of P gamma. So basically, given any loop at x1, you can make a loop at x0 by following gamma, then doing the loop at x1, then going backwards along gamma. By thinking about that, you'll see you get an inclusion of the left-hand side into the right-hand side. You can also do the reverse, so you end up getting both inclusions, so natural equality. Okay, so this is interesting because it shows that we've looked at lots of different kinds of invariants of things, such as curvature and torsion. And curvature and torsion, they're local invariants. It's something which varies with a point in the manifold. And on the face of it, the holonomy group also varies with the point in the manifold because it's something you define at a given point. But in this sense, it's independent of the base point, so it's a global invariant. Okay, so the way to think about it really is that considered as a subgroup of GL K, R. So we identify ort of E x0 with GLKR, and we consider the holonomy group as a subgroup of GLKR, but that's not quite good enough. We need up to conjugation. Because if you're going to identify ort of EX0 with GLKR, you have to choose a basis for EX0, and a different choice of basis would result in conjugating your subgroup by some element of GLKR. So as a subgroup of GLKR up to conjugation, then now the holonomy group of nabla is independent of base point. Okay, so we've got the thing now as a subgroup of GLKR. Thirdly, the holonomy group of nabla is actually a Lie subgroup of GLK, R. So that's the fact that it's a subgroup is actually a Lie subgroup that it lives within the theory of Lie groups. This is a non-trivial fact. I've forgotten exactly why it's true. If you look in the nearly infallible book, it will tell you, I'm sure. I think there's some theorem possibly by Yamabe, which says that something like an arcwise connected subgroup of a Lie group is a Lie subgroup. But it's some basic fact about subgroups of Lie groups which makes this true. So therefore, you can use the theory of Lie groups so fourthly, if X is simply connected, then the holonomy group of nabla is connected. As well, you can shrink loops. So if you've got any loop gamma here at x0, you can shrink it through loops based at x0 to the constant loop, and by considering such a thing, you'll see you get a continuous path from the parallel transport of gamma to the parallel transport of the constant loop. The parallel transport of the constant loop is the identity. So this means that there's a continuous path from any element in the holonomy group to the identity, which means that the holonomy group is connected. More generally, if we write hol 0 nabla for the connected component of the holonomy group, hol of nabla, containing the identity, and then, well, so then this is called the reduced holonomy group. So this is a normal subgroup of that. So we can form the quotient group. And by working on these kind of ideas a little bit, you find that there's a group. Okay, if you look at the fundamental group of X, there's a natural morphism from the fundamental group of X into the quotient group of hol of nabla divided by hol 0 of nabla, and this is actually surjective group morphism. And because we assume that our manifolds are second countable, this fundamental group here is actually finite or countable. So the holonomy group itself is an extension of the reduced holonomy group by a finite or a countable other group, which is a quotient of the fundamental group of X. Okay. Right, so that's all I want to say for now about the holonomy group of general vector bundles and connections. Now I want to move on to talk about the holonomy groups of Riemannian metrics, which are just the holonomy groups of Levi-Civita connections. So let's have a section 2.2 on Riemannian holonomy groups. Okay, so if we let X and G be a Riemannian manifold, with, let's say, X connected, so that the holonomy group is well defined. Otherwise, you'd attach a different holonomy group to each connected component of X. And if we let nabla be the Levi-Civita connection of which is a connection on tangent bundle Tx over x. So, well, we fix a base point is let 0 in big X, though we don't really care about it too much. So then we have the holonomy group so we define the holonomy group of G just to be the holonomy group of its Levi-Chivita connection. And this is now contained in the automorphism group of the tangent space at x0 to x, which is GLNR if n is dimension of x. And this is what we're going to be interested in. So tomorrow our main topic will be Berger's classification theorem, which tells you what are the possible values which the holonomy group can actually take. So for the next few minutes I just want to talk about a few more general properties of holonomy groups. Okay, so, well, we call this the Riemannian holonomy group. Okay, so one of the important things that holonomy groups do is that they measure the constant tensors. So let's talk about holonomy groups and constant tensors. Okay, so let's suppose you have some tensor S in the sections of some tensor bundle, tensor to k Tx, tensored with big tensor to the L T star of x. So as general a tensor as you like. So let's suppose this is a tensor on your Riemannian manifold X, which is constant under the Levi-Chivita connection. So with nabla a big S equals 0. So that is S is a constant tensor. So it's constant under the Levi-Chivita connection. Well, if we let gamma going from 0 into 1 into x be a piecewise smooth map so then the parallel transport map p gamma going from the tangent space at gamma of 0 to x into the tangent space at gamma of 1 to x. That's an isomorphism. This maps S at the point gamma of 0 to S at the point gamma of 1. Well, so that's an isomorphism. It induces isomorphisms between all the corresponding tensor bundles or tensor spaces at gamma of 0 and gamma of 1. And under these induced maps of tensored spaces, you get that maps to that. Basically because well, p gamma is constant along gamma. So p gamma works by essentially extending vectors in a way constant under the Levi-Chivita connection, and S is also constant under the Levi-Chivita connection. So you can think about S as being built out of some basis of constant vectors, really. So hence, whole of nabla preserves S at the point x is 0. So if gamma was a loop based at x0, then p gamma, which is an element of this, preserves the tensor at x0. Now this is actually a one-to-one. This is the converse. So conversely, if S in the tensor to the k of t at the point x0 of x tensored with tensor to the L of t star at the point x0 to x is invariant under the Lonely group of gamma, then there exists a unique S in the sections of this big tensor bundle with nabla of S equals 0 and S at the point x0 is S0. Sorry, let's make that an S0. So to see this, if you want to define S at an arbitrary point till x, you choose a path, gamma, going from x0 to x, and you define S at the point x to be the parallel transport along gamma of S0. Okay, so, but then you want to know, does that definition of S at the point x depend upon the path gamma you chose from x0 to x or not? And the answer is no, because if you had two different paths, gamma 1 and gamma 2, going from x0 to x, you could compose them in the opposite order and get a loop. And S0 is invariant under the parallel transport around the loop by definition, because that lives in here. And therefore, two different paths from x0 to x will give you the same S. And okay, you need to work a little bit harder to say that S is smooth, but it's true. So this gives a... Okay, so there is a one-to-one correspondence between constant tensors S on x under Lebedev connection and tensors at the point x0 invariant under the Lonely group whole of G. Okay, so the Lonely group is really measuring constant tensors. It's kind of what it does. And almost all of the Lonely groups, you can characterize them in terms solely in terms of which tensors they fix or which tensors they preserve. Okay, so well, one immediate corollary is that since the Levi-Civita connection nabla has nabla of G equals 0, and your Riemannian Lonely group preserves the metric G at a point. So a corollary the Riemannian Lonely group whole of G preserves G at the point x0. So we can regard whole of G as a Lie subgroup not just of GLNR, but a Lie subgroup of the orthogonal group O of n, which preserves the standard Euclidean metric at the point, and this is unique up to conjugation, not in GLNR, adductor conjugation in O of n. Okay, but somehow interesting holonomy groups preserve not just the metric G, but also other tensors, and it'll be interesting to see which other tensors can be preserved by holonomy groups, which we'll go on to tomorrow. Okay, so let's stop there.